Hey guys, so I'm here gonna just quickly show you how to use CEA, which is Chemical Equilibriums with Applications. So it's software developed by NASA for analyzing combinations of fuels. It can do other stuff too, but we're just gonna use it to analyze fuel combinations. So let's do the Quasar engine, which is the name of the engine for the Defiance record-breaking rocket that we are building. For those not on the team, potentially seeing this on YouTube, this is a tutorial that was originally made for the members of the University of Toronto Aerospace Team Rocketry Division on how to use this piece of this online tool that NASA created. Originally, it was not online. It was I don't remember when this was made, but I have a feeling this was potentially made like before or while the internet was being created. So it has a feeling that it was at one point very old and very difficult to use, and this was a very quickly thrown together UI for it. Anyway, so we don't need to change anything on this first page. You just click Rocket. Output, this is just the output style. So long and a short, those are data types. Basically, it gives you how many decimals, pretty sure. Don't know what debug does, don't need it. Output, we want, this is a more output settings. Do you want kilocalories per mole or kilojoules per mole for the values that use these? We want kilojoules per mole because, come on, who uses calories? Like, honestly, I hate calories. Just, they're, I hate the unit. Anyway. um, Output species, species being gas species, so and fuel species. So this is regarding the fractions of the different chemicals involved. Do we want the fractions of the moles of the gas of each gas slash fuel and propellant, or the mass fractions? We want mass fractions because we just end up converting mole fractions to mass fractions anyway. There's some cases where you'd want the mole fraction, but you can just, it gives you the molar masses, so you can just calculate those yourself. Mass fractions are more immediately useful. Anyway, so ions, nope, don't need them. Transport properties, nope, don't need them right now. Okay. Oh, and before you submit, you have to give it some kind of four-letter or four-character alphanumeric code. So let's just do test and submit. So this first page is where you put in your combustion chamber pressure. You can do this in any units you want that it offers. You can do up to 16 unique ones or do an incremented value. It has to add up to 16 increments though, so you do low value, high value, and the increment. Um, you can do it in megapascals, kilopascals, atmospheres, bar, PSIA. I've gotten used to bar. I used to prefer PSI um, because that's just what I had. That's just what we've used for a while, but I've recently started switching to bar because it kind of gives a nice scale of engines. So like smaller engines, like our scale of engine, or a lot of smaller vacuum engines, um, or yeah, the kind of not orbital lifting engines. Uh, these kind of, and so, like a lot of missile engines too, are in the tens of bar, whereas big orbital engines such as the Merlin or the F1 from the Saturn V rocket, or the Raptor, um, are in the hundreds of bars. So the Raptor, I believe the goal that SpaceX has for the Raptor is somewhere like 300 bar, whereas ours is, well, I know it in PSI actually. I don't know it in bar, but the output will be in bar. No matter what you put in, it converts everything to bar. So that's kind of why I got used to it. But anyway, PSIA, and keep in mind this is PSIA, not PSIG. So if you have, so for instance, I know that our engine, the Quasar engine, is 450 PSI, but that's PSIG, so gauge pressure. So I need to add about 15 PSI to that. So let's do 465 PSIA and submit. So you can do monopropellants, you can do solid propellants, you can do, or you can do fuel combos. We're going to do a fuel combo, but if you did the monopropellant or solid propellant, um, it only has preset monopropellants and solid propellants. You can't pick your own. Rather, you can't pick unique combinations of solid propellants and monopropellants, it only has a few set ones. You can't do a monopropellant by just picking one fuel because you can't not pick an oxidizer, and if you pick the oxidizer to be the same thing as the fuel, it won't converge in its calculations. I'm not totally sure what calculations it does. I haven't looked into that. Um, yeah, but I've tried it and it doesn't work. So we are going to, though, we want to use a hybrid rocket, a paraffin nitrous hybrid rocket. So we're going to use periodic chart because liquid hydrogen, nope. RP1, nope. Neither of those are what we want. So let's use the periodic chart for our fuel. This is just for the fuel, so not the oxidizer yet. So we want to we want to know the chemical formula for paraffin. So paraffin wax. Let's find, okay, CnH2n plus 2. We don't really need to know the exact amount of CnH, just that it's got C and H in it. So let's click C and let's click H, carbon and hydrogen, submit. So then it gives you, based on your constituent elements, it gives you a list of all the different fuel options that it has those and only those constituent chemicals in any amount, in any quantity. Uh, it has to have both. So notice hydrogen is not here. So it wouldn't just do hydrogen, nor is carbon just here. Yeah, so what we want is paraffin. By the way, it has, if it's not on here, you're boned. There's nothing you can do about that. If it, I mean, I can't imagine any fuel that you could pick that wouldn't be in this program because, for fuck's sake, they've got styrene. I have never heard of a rocket that uses styrene as a fuel, or pentane, or isobutane, or uh, cyclobutane. Wow. I Yeah, it's got everything that you'd need. So anyway, we're gonna click paraffin. We're gonna hit yes, use checked fuels. Do we want anything more than paraffin? No, we don't want anything more, so we hit yes. We hit submit. So then we want the oxidizer. So thankfully ours is right here, nitrous at 298. By the way, gases are listed as just like, if I wanted fluorine gas, it would just be F2. If I want liquid fluorine, I'd have to have that L next to it. The exception are things like nitrous, which are usually stored as a liquid and used as a gas, or injected as a sort of mixture. Well, in our case, we cavitate the nitrous through the injector plate, so it kind of injects as a uh, partly gas, partly liquid spray. Um, anyway, we're just to demonstrate again the use of the periodic table. We use the periodic table, submit. So nitrous has N and O in it, so we submit just with N and O. So then it gives us these options. We pick nitrous, we submit. Do we want to use any other oxidizers? Nope. So we submit. What's our starting temperature? So this is not the temperature of the nitrous as it's entering. This is not the temperature of the nitrous that's like burning, because it's gonna calculate that. This is the entering temperature, so the starting temperature of the nitrous oxide. So we're going to hit, we want 25 Celsius, and yep, that's pretty much good. So, OF ratio. This is one of the few things, like the chamber pressure, this is something that you need to know prior, or you need to have a list of them. Same with chamber pressures, you can investigate a few different ones um, to see the difference and analyze what the best ratio for your situation would be. As I'll go over in another video, the grand trick to doing preliminary design of a rocket and a rocket engine, because there's so many equations, and basically it's an open system when you start. So you got to basically kind of pick some values based on your goal, based on your situation. You have to pick some values to kind of assume, just basically kind of fudge a bit. Not so much fudge, but based on maybe like past examples or past designs or other constraints of your situation, pick certain values to fix or to assume, and then once you've fixed enough of the values, everything else falls into place like dominoes. Eventually, the system becomes defined and everything falls into place. Um, yeah, and then if your final result doesn't achieve what you're trying to achieve, you go back to your initial assumptions, tweak them a bit, and you try again. Uh, that's yeah, that's kind of basically the only way of doing it that I've found. So we already know our oxidizer ratio, so let's do 4.5, or oxidizer fuel ratio rather. So that's, and you can do the whole thing, so you can submit multiple oxidizer fuel ratios and multiple pressures, which would give you this a ton of data. Basically, you could use that to generate a, not, you'd have to strip the data from the output file using a script, but you could effectively at the end of this, the output of your script, generate a 2x2 array of the combustion chamber gas properties based on varying chamber pressures and oxidizer fuel ratios to analyze a given fuel combination over different scenarios. Then you can repeat this process for a different fuel combination. So then we don't need to do that here though. So let's submit this. So here's where you can find the properties at different parts of the nozzle. So you can do that by putting in the subsonic area ratio, so what point in the nozzle prior to the throat, what point in the nozzle past the throat, so the supersonic area ratio, um, and or you can do the chamber pressure over the exit pressure. So at what point, uh, at basically, yeah, so you can pick different exit pressures, which is to say basically like different altitudes. So you have to find what altitude you're looking for, put that pressure in. You don't have to. It already assumes that you're trying to go for perfect expansion. I believe so. If not, you can put in what expansion you want. I'm just going to leave it blank for now, so let's submit. So you can leave everything here the way it is. Okay, so we get input file and output file. If we just want a quick look at what these are, and it's just kind of one-off, we can ignore the input file, but if you want to keep track of a bunch of different inputs, I would, one, name the starting thing something iterable, so like A1, B2, A1, B3, A1, B4, that kind of thing, if you have a lot of output files, and then keep track of your input files as well, so download both. For just one-offs, we can just ignore the input file, and by the way, .inp and .out are not real file formats, they're just texts, which you can copy and paste into a text file. So we just had one pressure and one oxidizer fuel ratio, so we only get one of these charts. If we did two pressure ratios, or not pressure ratios, sorry, two chamber pressures, we'd get this plus another copy of it below it. If we did two chamber pressures and two oxidizer fuel ratios, we get four of these. One here, and then two more, like one here, and then three more below it. Yeah, because 2 times 2 is 4. If we did three oxidized, well, yeah, you get the point. It does every combination of the choices that you made. So here we have, or let's start up here. So up here you have input parameters. You can basically, the important stuff starts at this line. So we have the starting chamber pressure in bar, and at the chamber pressure at the third. Okay, so yeah, it doesn't calculate the perfect. Oh, of course it doesn't. No, because perfect expansion is going to depend on the. Sorry, brain fart. It doesn't calculate the exit pressure because we didn't put in an exit. It doesn't calculate the exit pressure because we didn't put in an ambient pressure, which would be done in the PC over PE section. My bad. Anyway, so we've got pressure in the chamber and at the throat, so at choking. So when the nozzle is contracted to the point where the fluid velocity is at Mach 1, this is what the pressure will be in bar. Then the temperature at these 2 points, the kind of not the wall temperature, the not near wall temperature necessarily, but the kind of bulk temperature in the body of the fluid. Um, the density, rho, it gives the units next to the variable name as well. Then we get hugs. Enthalpy, internal energy, I can't remember what G is, and entropy. I, yeah. Um, we can ignore these for the most part uh, because that's not what we're looking at right now. Unless you need these, in which case they're here. Um, anyway, moving on. Then we get molar mass. So how many grams per mole? Uh, here we get 23 grams per mole for the chamber, and at the throat we get 23 point, well, basically 23. It changes only by a tiny, tiny bit in this case. And in most cases, it doesn't really change that much. Then we get these values here aren't too important for many applications unless, again, unless you're doing something really specific or looking at some really specific analysis. But if you're just trying to look at a general uh, kind of overview or analysis of the combination, we don't really need that right now. CP, for the most part, in the equations for isentropic flow, the only thing that you really need CP for is so you can calculate gamma, but they already do that for you, which is right here. Sonic velocity, meters per second. So this is the speed of sound at that point. The speed of sound is not uniform as the gas is expands through the nozzle. Yeah, so it tells you that at every point that you've asked for. And you can put more, if you put more of those supersonic, subsonic area ratios or pressure ratios, it'll put more columns. And then we get to performance parameters. So C star is an important one because that is independent of your nozzle. It's purely a function of the properties of the combustion in the chamber itself. CF, I'm fairly certain this is a function of the nozzle, so it kind of, I'm guessing it uses a 15-degree angle cone nozzle, because that's the usual baseline comparison. Then we get ISP down here, which is just C star times CF, no, sorry, C star times C tau, but it doesn't give C tau. Anyway, let's move on. And then here we have all the different species of exhaust, which is all the different gas species. Not necessarily all of them, but all the ones it calculated for. Yeah. And yeah, so that's the output file. That's what you get. So the important ones you got are gamma here, which is your ratio of specific heats at different points. Does change, not by a lot. So like in theory, you could assume it was constant, and if you're just doing calculations on paper, assuming it was constant, at least up to the throat, wouldn't be wouldn't be a gross exaggeration, but in reality, that wouldn't hold up in reality. So yeah, thinking that sonic velocity is the same is obviously not at all correct. Yeah, so gamma is an important one. Molar mass is an important one. What else? Density, that can be useful. That is useful rather, not. Temperature, of course, vital, and pressure, absolutely vital. Then you get at different, what is the area ratio of the column? So this is ratio to the throat. So area, it says AE, area exit, but what it means to say is the area in question. So it assumes that that area is the exit. Oh wait, I just did air quotes. I'm an idiot. Yeah, so quote unquote exit that in question here. But it doesn't have to be the actual exit. It can also analyze, as I said before, subsonic area ratio, so parts of the nozzle prior to the throat. So yeah. Anyway, this is how you use it. You can do it for other fuels, liquid fuels, gaseous fuel mixtures. You can do bipropellant like we did here, or tripropellant, quadpropellant. I don't know any quadpropellant, and the only tripropellant I know is actually physically impossible. It's the liquid lithium, liquid helium, and one other thing that's crazy. Fluorine. Yeah, that's what it was. um, Rocket, which produces a gas, exhaust gas hotter than can be contained by any material that we know of, but is theoretically the most efficient, um, or I can't remember if it's the most efficient or most powerful fuel. I think most powerful. But anyway, yeah, that's how you use chemical equilibriums with applications. Hope this helps. Anyway, see you guys.